Swayam Prabha. Digital India. Educated India.
Let us continue our discussion on Carnot cycle and some of the conclusions that we may draw out of these things. So, what we have shown that Carnot cycle is a reversible cycle and plays a pivotal role in the context of thermodynamics, and so this Carnot cycle is a reversible cycle and it is a this reversible cycle has certain characteristics that this is basically considers a system which is connected to heat reservoirs, one at a temperature T1 and another at a temperature T2. System has a working medium and it draws Q1 amount of heat from the reservoir T1 and put it in Q2 in the T2 reservoir, and we get W amount of work from the system. So, W equal to, and this since it is operates over a cycle, then it is Q reversible. More specifically, I like to write that Q reversible, Q1 reversible and Q2 reversible. So, basically this is Q1 plus Q2, and for the reversible cycle we attach this thing. So, this is basically the first law of thermodynamics that is embedded in the construction of Carnot engine, and that is one thing. And secondly, the system, the entire considerations are based on the all is based on independence of the material medium used in the system or engine. So, material medium, so all these all considerations are based on independence of the material medium used in the engine or system, and that is a very important thing, that whatever system I am using is not important. What is important is the temperature of T1 and T2. And so, what we showed that we had the efficiency eta is basically 1 plus Q2 reversible divided by Q1 reversible. That was the thing. And we also showed that Q1 and Q2 have opposite signs, and furthermore we had the functional form. The functional functional form of Q2 reversible divided by Q1 reversible is basically T2 T1, and we showed that it is basically minus T2 by T1. So that was a very important result that we could prove it. The functional form of this, the ratio, is a function which is basically just a ratio of T2 by T1. And so I can rewrite. So with these are the basic considerations which is needed for our further analysis, and we will draw certain conclusions out of this out of these things. And also there is another point, that the efficiency of an reversible engine is always greater than efficiency of an irreversible engine. So these are the conclusions that we know and we have got purpose. So now the conclusions from these items we can draw is the following. That is, we first redefine this, that eta can be redefined very clearly as Q T2 by T1, and you can see the efficiency increases as we lower the temperature of the sink. This is the sink. See, the T2 is called the sink, and this is basically the source. So heat is drawn from the source and dumped into the sink at T2. So only important thing is the temperature T2, T1 and T2. So if we eta increases, that means if the gap between the source and the sink temperatures are made large, then the eta increases. So you can build up more efficient engine. That means your petrol, your diesel engine will be more efficient than an petrol engine. So because the ignition points are higher in the case of diesel. So that is one of the conclusions. So this is a very fundamental formula used for defining our efficiency of a system. So that's fine. The second conclusion, another conclusion we may draw from this equation, this functional relation, that we know that Q2 reversible by Q1 reversible equal to minus T2 by T1. So this was the conclusion that we derived the functional relation, and the reversible condition must be maintained. And so this I slightly rearranged it. Q reversible by T2, that is equal to minus Q1 reversible by T1. Now I can still rewrite it in this form: Q2 reversible by T2 plus Q1 reversible by T1, that is equal to 0. Now if these are for finite steps, but for reversible thing, if these are added in very, very small quantities, then in such a way that there is no change in the surrounding, because the reversibility condition is maintained. So I may write it as, so this is basically a sum over the heat drawn from the heat exchange with T2, heat exchange with T1. So, Q2 by T2 plus Q2 by T1 and so on. You can add other engines, and if you add it, then finally this result is equal to 0. So, if I write it as a sum or an integral, since it is a cyclic process, this conclusion, everything is based on a cyclic process. A cyclic integral tells us that is the Q reversible by T equal to 0. So, this is can be directly written in this form, because you know that this is operating on a cycle. So, this is a cycle, and since it is a summation of such terms, small terms, I am using the summation of these terms, and for each case I divide it by T, and so this is a quantity for each of these piece. So, this is ultimately gives you 0. Now, the very interesting thing is this, that we have got a cyclic integral of a function of a differential which is 0. Now, any cyclic integral, if it is 0, then this must be a function. If I write this as ds by ds, so it is means equal to 0. So, where ds is a differential of a function s, it is dq, but a reversible sign by t. Note that dq itself is not a differential, but dq reversible by t behaves as a differential. So, differential of a function s. So, there exists and that is equal to 0. So, so if this is true, and if ds is a differential, true differential, or if this means that ds is an exact differential, and this leads us to a new function, thermodynamic function, and that function is S, and we call it entropy. So, second law gives me a very interesting quantity, a new function like internal energy, enthalpy. We got a new function that is called entropy. So, that is a conclusion that we draw from this consideration. That is a conclusion. And but note that if it is irreversible, then we cannot write such a relation. In that case, I cannot write. So, just a note that dq irreversible by t is not equal to d of some x. This is not, we cannot write it. We cannot write this kind of function, because this is always inexact differential. dq irreversible by t, you cannot write it as a differential of some function x. You cannot write it. That's why I have put it not equal to. So, such a thing cannot be written. So, keeping that in mind, that when dq reversible has a special status, so dq reversible by t is a new quantity for us, and this is a of course a function, and since the integral is 0, that means I go from one state to another state and come back to this state. The overall integral is 0. That means it is a state function, and so the function is a state function, like as we mentioned, internal energy and enthalpy. So fine. Now, what about the what about the irreversible path or irreversibility? So conclusion again, for irreversible path, what about dq irreversible by t? So that is another question that automatically we must raise. So this is the following. We again start from this case, that is Carnot theorem, that tells us that we know that efficiency of a reversible engine is always greater than that of an irreversible engine. That means eta reversible is always greater than eta irreversible. So I may write as 1 plus eta may be written as Q2 reversible by Q1 reversible greater than 1 plus Q2 irreversible divided by Q1 irreversible. This automatically follows from the definition of the efficiency. So if this is so, then I can write that Q2 reversible by Q1 reversible is greater than Q2 irreversible by Q1 irreversible. So what follows immediately is that we may rewrite this from this conclusion, that we have an equality that we already know, since Q2 reversible by Q1 irreversible equal to minus of T2 by T1, that we have shown as a functional form of the ratio of the heat Q2 by Q1 when they are taken in an exchange in reversible way, then we have a minus of T2 by T1 ratio. So if this is so, so we may write, we replace this part, so it is minus T2 by T1 greater than Q2 irreversible by Q1 irreversible. So this means I can slightly again rearrange it, minus Q1 irreversible by T1 greater than Q2 irreversible by T2. So if I write it in this way, or I can take it on the other side, Q2 irreversible divided by T2 plus Q1 irreversible divided by T1. If I take it on the other side, the sum is less than 0. That is a negative quantity. Okay. So this means that now again, if I write this as a sum, as a cyclic integral kind of thing, then with dq, with inexact differential dq irreversible by t is now a quantity that I can see, but dq irreversible are small increments for each for temperature T1, for T1, T2, etc. And that is less than 0. You see that for when dq reversible, the integral is 0 and you got a new function. But such a we are not actually getting such a situation when dq irreversible is actually an inexact differential. So we cannot write it, we can replace it by a new function. So new function like dy, d, sk, so we cannot replace it. So this is, say, if this is 1, then it is 2. I can write both this condition. So together with dq, if I write it dq by t, which must be less than or equal to 0. It means I include together with reversible equal to 0, dq by t is a general form of writing, and it means that whenever you have, when dq is reversible, so for reversible case, dq equal to dq reversible by t equal to ds, and in that case equality holds. So in that case this equality holds. That means this equality holds, and for irreversible dq by t irreversible, we have this condition less than 0. So together this thing we may write it in this way. This is another kind of inequality. Wherever see that there is a irreversible change, we have to describe it in terms of an inequality rather than equality. So far so good. Now we come to another interesting conclusion, which is the following. So another conclusion, suppose a system undergoes a cyclic process. A system undergoes a cyclic process in this way. A goes and B, there are two states, A goes B, and say reversibly and B goes to A irreversibly. So, I have chosen a path such that I go from A to B through a reversible path and come back to my original A, that is irreversible. Now, so what should be the thing? So, we know that for dq by t is less than or equal to 0. This is my general conclusion. When dq is not specified, because for this part, entire cycle becomes irreversible. If the part of the cycle is reversible, that doesn't mean the cycle is reversible. Entire cycle is irreversible. So, this condition holds good. So, this means that irreversible path, if this is now, if I break this cyclic integral in a form that I go from A to B, where dq is taken reversibly by t, then from B to A, dq irreversibly by t, that is less than or equal to 0. Now, this is a quantity, it is basically ds. This quantity is ds. So, A to B ds plus B to A dq irreversible by t equal to 0. Now, you see there are the two limits are, this is from A to B, B to A. What I do, I interchange the limit. Just interchange the limit means there will be a minus sign here, interchanging the limit B to A ds plus B to A dq irreversible by t less than equal to 0. Okay. So, now the two integrals are same, B to A, and this is ds. So, if I take it to the other side, so you see that integral ds is greater than or equal to integral dq irreversible by t. So, if you remove the integral, this is the B to A, then ds greater than or equal to dq irreversible by t. This is another celebrated relation in thermodynamics, and this is called the Clausius inequality. This is called so equality means that you are maintaining equality arises when you have the irreversibility becomes reversible, otherwise the ds change of ds is always greater than dq irreversible by t. That is the conclusion. And for a reversible path, of course, ds equal to dq reversible, so it becomes irreversible becomes reversible. Otherwise, such a conclusion cannot be made. It is important to note that ds is always greater than dq irreversible by t. That has to be, but this is for a single step B to A, or this one for a single step ds is greater than this one. And okay, so now if it happens, now a special case of this is the following. Suppose I take an isolated system. For an isolated system, where nothing is allowed to enter. So, isolated system means you have a system and boundary is there, and there is a surrounding system. So entire thing is an isolated system. So that is it means system plus surrounding, isolated. So if it happens that dq is equal to 0, for isolated system, nothing is entering into the system, the dq equal to 0, then ds is greater than or equal to 0. It means what? It means that when we are for irreversible path, for irreversible condition, ds will increase, ds greater than 0, it means it will increase. Entropy goes on increasing, but for reversible path, reversible condition, ds equal to 0 means s does not change. S does not change and it has attained a maximum. So this is the condition for an equilibrium of a system. When of an isolated system, the total entropy change is 0, that when the system has reached a maximum. So with this several conclusions, we conclude this session also, and in the next lecture we will go over to discuss several properties of this new function entropy. So thank you all for your kind attention.